and enjoy the talk. Thank you again for coming.
Thank you, Sergey. Hey, thanks. This talk might run a little long. The plan was 90 minutes, and then I was told I have 60, so I apologize for that up front. It was great. I kind of got my career started. I worked at Apple in, 88 to 93. And I got my start at Apple because I went to a conference and sat down with a senior engineer from Apple and said, hey, I've read your article. Would you want to work on a hack? The conference was called Mac Hack. Do you want to work on a hack together? And he said yes. And that turned into a job at Apple and kind of launched my career. So now when people ask me to talk, I try really hard to say yes. I don't always, but I do try to say yes. I think it's my time to kind of pay the community back. I'm a senior principal scientist at Adobe. Depending on how you count, I've been at Adobe a little over 30 years. I joined in '93 after leaving Apple. The reason why you could count differently is I did work at Google in 2009 to 2010 on Chrome OS. So I have a little experience with the company here. I right now have the best job, I think, in the world, which is I work in the Software Technology Lab, which is a group I created for the second time. This is kind of the Software Technology Lab 2.0. And my job is to try to plot the course on improving software development practices in the industry. And so I could have fun and write code and papers and hopefully a book someday, all the time. So almost 20 years ago, at the very first BoostCon, which was held in 2007, before it was known as C++ Now, I gave a keynote titled The Possible Future of Software Development. And that resonated. But it actually came from a talk that I first gave at Texas A&M, where Bjarne Strustrup was working as a professor, and Bjarne asked if I would go and give a lecture there. And that was part of Texas A&M's industry affiliates program. And so there were lots of people from lots of companies there, and I ended up giving this talk at IBM and Yahoo, Google, and at Google it was actually recorded into a tech talk. Lockheed Martin, so a number of times in a number of places. So the only recording that I know of is the Google one, so this is me. I never mentioned in this talk, but the shirt I was wearing for a reason. It was from Lockheed Martin, so those are actually planes on there, and I gave the talk to the F-35 Joint Strike Fighter team, and we had some really interesting conversations after. But that's me giving the talk, so possible future of software development. So I thought now we're almost 20 years later, Dave Abrahams on my team said, oh, you should re-give that talk, because 20 years, a lot of people weren't even born yet. And it was a good talk, and so I thought, well, let's not just give the same talk, let's revisit it, and that's why we're here. So I started this talk, since it was to students, talking about where the industry was and where Adobe fit into the industry. So I thought it would be interesting to take a little bit of a look there. Back in 2006, when I first gave the talk, there were 6,000 employees at Adobe. Now there are upwards of 30,000. Our revenue was about $2.6 billion. Now it's about $22 billion. If we look at Photoshop, which is the product I've worked on and around for most of my career at Adobe, there were 20 engineers on Photoshop in 2006, and in 2025 there's about 250. Now the interesting thing is quality engineers did not scale the same way. There were 30 to 60. I think that is very unfortunate, but it is the case. The platforms we supported were just Mac and Windows, and now we do Mac, Windows, Linux on the server side, iOS, iPadOS, browser, WASM, and the ... there should be Android, which we just announced and shipped recently. In both time frames, we have a whole bunch of shared technology groups, but they've been completely nuked and reorganized multiple times, so I had no way to draw a comparison other than to say, yes, we had them. Our process back in 2006 was very waterfall and 18 to 24-month release cycles. And it wasn't because we didn't know how to write software in a better method than waterfall. It's because at the time, the Photoshop book counted as a bestseller, and our CD would be considered, a gold record. And so we had to book time with publishers, both to manufacture the CDs and to print the book way in advance. And so we had a long lead time, which means we needed to have all the copy for the book done way in advance. And so the first draft had to get to the publisher about 6 months before we shipped. And that means we needed all the artwork and all the screenshots and everything in the book. And so that pushed us into a waterfall model where we would sacrifice quality on the front end and then try to fix all the bugs in a slog on the back end. So it was pretty brutal. Now we're much more agile-ish, I would say. We don't follow a formal agile process, but we do release some version of Photoshop every couple of weeks. So what were the analysts saying back in 2006 about the future of software development? Well, Gartner Research had this to say. Organizations need to integrate security best practices, security testing tooling, and security-focused processes into their software development cycle. Proper execution improves application security, reduces overall costs. I thought this was very interesting because we're talking a lot about memory safety and about security still today, 20 years later. So I don't think we're there yet on this point. This quote back in 2006 I just found immensely humorous, which was that Microsoft has been slowly moving to a new development process, and then the new process should help Microsoft gain more feedback early in the development cycle, but won't necessarily help the company ship its products on time or with fewer bugs. Wow, okay. And that was published by Microsoft. So I just thought that was humorous. And back in 2006, I pointed out why I thought the status quo on how we develop software will fail. And it comes down to this from 1986. This is a quote from John Bentley, who wrote an article in ACM called Programming Pearls. And one of his articles, he said this: I've assigned this problem, it's a binary search problem that he's talking about, in courses at Bell Labs and IBM. Professional programmers had a couple of hours to convert the description into a programming language of their choice. A high-level pseudocode was fine. 90% of the programmers found bugs in their programs, and I wasn't always convinced of the correctness of the code in which no bugs were found. Okay, binary search. Professional developers, 1986, so 30 years ago, had a really difficult time with this problem. Mark Hamburg, who was the first Adobe employee to work on Photoshop, Thomas Knoll and John Knoll originally wrote it, read this article and said, I want to hire the 10% who can do this. So Photoshop to this day has a take-home test, which is a binary search problem. It's a one-page description of a problem. The answer happens to be binary search. We hand it out. You can write it in any language you want and bring it back. In the let's see, I joined in 93, so between 93 and today, I'm sorry, that's almost 40 years ago. Wow. Okay, between 93 and today, so over 30 years, we've had 2 perfect answers. One of them turned down the job offer, but the other one, she's an amazing engineer, still works at the company. So this was John Bentley's solution to the binary search problem. This is what he wrote. This is not a great answer to a binary search problem. Okay? First, you're throwing away information. Okay, when you find it. You went through all the effort to find a location for where the item could go, and then you threw it away. It has a potential integer overflow right here. Okay, it has an additional comparison on that line, which is unnecessary, and will just slow the algorithm down. And it's requiring signed integers, also with a -1 up there, as opposed to working with unsigned values. So this would be a better solution to binary search. This is what I had on my slide in my 2006 talk, right? Name lower bound, some of you might recognize it, okay? So, but this is just concrete, a non-generic implementation of lower bound. So that's what a good answer should look like. So this raises the question, if we can't write binary search, John Bentley's own solution is considerably more complicated and slower, then how is it possible that we build applications, Photoshop, Acrobat, Microsoft Word, Google, right? How do these things exist if we can't write a very simple fundamental program? Right? And I'm going to leave that hanging for a minute, and we're going to step forward. So what do the analysts say the future is now? Well, I went and did some look. Almost all developers will increase their usage of generative AI and machine learning as code assistants and low-code, no-code tools proliferate. Okay. More than 55% of developers, I found this amazing, this was a year ago already, automatically generate 40% or more of their code in their IDEs, highlighting the widespread use of generative AI and machine learning in software development. Okay, so how does Copilot do on the binary search problem? Amazingly well. Okay, that's a correct implementation of binary search. It's almost token for token identical to my implementation. So maybe it learned from me, I don't know. And I asked it, I said, well, okay, binary search insert position. The reason why I came up with that name is because that reflects the actual statement of the problem. And I said, how would you improve this? And one of the suggestions it said was, well, the algorithm name should be better. It says the function is essentially an adaptation of stood lower bound. Now, the interesting thing is the Photoshop team will accept stood lower bound as an answer to this problem. Okay? So not only did it write the code, but it recognized from the description of the problem that this was a lower bound problem. So that's the end of my talk, right? I mean, clearly we're done. Okay, I have a little more time. So let's keep looking here. Okay, so we had this question hanging there. How is it that we write software today? So this is looking a little bit at the waterfall model. This is a graph from all bugs on 2005. Actually, it spans a longer range from, it looks like, that's March 2004 up until August 2005. These were bugs in a major Adobe product. Okay, so the interesting thing I want you to look at is the red line here. Okay, so the bugs climb up, climb up, climb up, climb up, and then this section, they're almost linearly going down. Okay, how is that possible? You would kind of expect this to follow a bell curve, right? To go up and taper off if you were following a waterfall model. So what happened here? Anybody? Anybody know? What's that? A what model? No, it wasn't a switch in process. He said maybe agile model. Maybe we switched in the middle there to a different process. Maybe. What actually happened is we realized that the graph was going to overshoot the ship date. This is the ship date right here. Okay? And so there was, first, get everybody into the office over the weekend and drive the bug count down. So that's that first little dip. And then get all of QE in over the weekend to test, and it goes back up. Okay? So now we're going to start deferring bugs. Okay? What bugs do we not have to fix to get to ship? Okay. So that's a deferral line. That's what that looks like. Okay. So this graph reflects my inability to get a decent graph out of Jira. But I thought that this was somewhat interesting nonetheless. So on the top here, it's mostly uninteresting, but what we're looking at is the number of created issues, the number of bugs opened up against the products, versus the number of resolved issues. Okay? And so the blue line here is basically the gap between those two lines going up. Now, an interesting thing happened. I took it back as far as I could within our database. I would have liked to have gone further. But right over here, okay, we were doing really good, right at about 0. An interesting thing happened, which is we greatly expanded the ecosystem. We first shipped Photoshop on iPad, and then we did it server-side, and then we did it on the web. And so we rapidly ramped up the number of engineers on the team and the number of products we were shipping out of the code base. And that had a serious impact on our ability to close bugs quickly against everything. You can see eventually we got a handle on the process, and so around here we started to flatten out. We still have a backlog of things to plow through. Okay, but let's take a further look here. So this is a graph broken down of what our bugs looked like. So that's how many bugs we fixed, 54% of the bugs. The red ones there, 9%, are marked as we won't fix them. That's because either that component is already being rewritten, and so we're just not going to go revisit it, or just because they were considered cosmetic or low priority enough that they weren't worth bothering with. Personally, I think that number's too high. Okay. And then the number of deferred bugs. Okay. So if you read the definition of deferred within, we have guidelines. When you defer a bug, what does that mean? And it says, we'll consider it a future date. And you can hear the narrator voice in the background going, no, they won't. Okay? Okay. A deferred bug won't be fixed. In fact, I had a previous manager who, at the end of each release cycle on a product, would just clear the bug database, and everybody would say, why are you doing that? We have all those deferred bugs to work on. He's like, if we didn't have to fix them for this release, we don't have to fix them for the next. So, yeah. So that's still a significant amount of bugs that are actual bugs, and if you scaled it against the fix there, you're looking at about almost 10% of your bugs are getting deferred, right, compared to fixed, because cannot reproduce or working as designed or duplicates, those are kind of not bug categories. So unresolved. Oh, I should point that out. Unresolved 9%, that's where that big gap is coming from, is we still have this backlog of bugs to plow through. Okay, iterative refinement. That's the answer. How do we ship software today? Well, our current programming methods lend themselves to iterative refinement. We don't solve problems. We don't write binary search, right? We rarely write correct code. We approximate solutions. We iterate until it's good enough, and then we ship it. Okay. So how could we write better code? Well, we want to study how to write correct software. We want to write algorithms once in a general form that can be reused. We want to focus on fundamental algorithms and compose larger systems from proven components. This is what I was saying 20 years ago. And that leads us to the topic of generic programming. Right? Back in 2006, the idea of generic programming was still young. In 2002, Alex Stepanoff, he's the person who coined the term generic programming and created STL and C++, gave a talk at Adobe. I attended the talk. If you watch the video, you can catch me sitting in the front row way on the right-hand side. After this talk, I pulled Alex aside and we chatted for each other, and that turned into Alex coming to Adobe, and we put together a team, the first incarnation of the Software Technology Lab, and managed to work together for 8 years. But Alex put up this slide saying, is STL successful? This is back in 2002. There were millions of copies already out. Everybody, Microsoft, IBM, Sun, ships it. Okay. There were a dozen books on the topic. There were very few extensions. what did Alex mean by an extension, right? What he meant was libraries written in a similar form, libraries that follow the principles of generic programming. There was no language progress. We didn't have concepts in C++ at the time. There were no other languages that were picking up these ideas. And he viewed it as, even though he wrote this great library, up through 2002, it had no effect on software engineering. Okay. So Alex still considers STL a failure, right? I strongly disagree with them, and I think that this line now is significantly changed. Okay, let's look at Alex's original definition of generic programming. This is from a paper written by David Musser and Alex Stepanoff. David was one of the collaborators on STL. He said, by generic programming, we're talking about algorithms and data structures, okay, that are abstract or generic, accomplishing related programming tasks simultaneously. The central notion is that of generic algorithms. The entire point of STL is about the algorithms. Everybody focuses on the data structures. It's a proceduralized, or it's a parameterized procedural schemata. What does that mean? It means that it's a way that we can define an entire family of solutions with one piece of code. Okay, that's independent of the underlying data representation, but it's derived from concrete, efficient algorithms. So that was his initial definition. What does that mean? Programming with generics is not the same as generic programming. Metaprogramming, not the same as generic programming. Right? Generic programming doesn't mean templates. Templates is just a mechanism that happens to be used in C++. Generic programming is mathematics. I mean that literally. So in mathematics, we have axioms. In generic programming, we have semantic requirements, which are expressed as axioms. Okay? In mathematics, you have algebraic data structures. In programming, we have concepts. Concepts is a term that Alex coined. Okay? But they are the same as an algebraic structure. We call models the same thing. Models are models. Models are instances of concepts. In math, you have theorems. In generic programming, we have algorithms. And what we refer to as a regular function, which is a function that always returns the same result for the same arguments, a little different than pure in that it's allowed to have side effects, so long as the side effects don't affect the result of the function. So those are regular functions. Mathematics has just functions. Okay? And when we're dealing with programming, we're dealing with complexity as part of the attributes of our algorithms, and mathematics doesn't really have a notion of complexity. Okay? So further, we can talk about refining a concept, which is a concept defined by adding requirements to an existing concept. So on the math side, you have the same idea, which would be refining an algebraic structure. So a monoid is a semigroup with an identity element. That definition works for both programming and math. A bidirectional iterator is a forward iterator with constant complexity decrement. Okay? So you would never see such a distinction in mathematics because you're not concerned with complexity. And a refined algorithm or a specialization is an algorithm performing the same function as another, but with lower complexity or higher efficiency on a refined concept. That's an important point, because the idea with generic programming is you could take any piece of code, no matter how concrete, extract the properties of it, and come up with a generic implementation of it. And at some point, you get down to the point where your requirements are so constraining that there's only one possible model, in which case you just have a concrete implementation. And through refinement, it means there's no place to get underneath generic programming. There's no opportunity to be more efficient than you can write with generic programming. And so early on, Alex published this Stepanoff abstraction penalty benchmark, which had a huge impact on compilers at the time. And it was showing how how if I just replaced a double with a struct that contained a double, that has a significant impact on the performance of everything, of all the compilers at the time. And he was like, that's unacceptable. It's just a double. It doesn't matter if I wrap it in an otherwise empty struct. And that was trying to get at this. How do we write code so that we have the maximum efficiency? So concepts. Let's look at why I say concepts are an algebraic structure. Right? A concept is a set of connected requirements. Okay? It's the connectedness that makes it a structure. That's why algebraic structures are connected axioms. So a concept is connected requirements. So if we look at equality is a unique equivalence relationship. And we spell out what the requirements are. Those are the axioms for an equivalence relationship. It's reflexive, it's symmetric, it's transitive. Connected to copy and assignment. Okay? So copies must be equal, copies must be disjoint. The concept of regular is essential for equational and local reasoning. In C++, the concept of regular is to say, okay, we want equivalence, we want copy, we want a handful of other operations. These are the operations that are, in some sense, defined for all types. They come from the definition of a type and the fact that we're representing that type as memory within a machine, and so the characteristics of the machine. That's where the concept regular comes from. So Alex had this vision that we could build a repository of algorithms. And I thought, it's never happened, not in the sense that he's wanted to see it, but we could model it after the IRMT. It would be a collection of fundamental algorithms and data structures presented in common form. Just like in the IRMT, it has fundamental theorems and formulas stored in a standard form. It would have proven implementations on a variety of languages. Just like in the IRMT, it has both manual and automated proofs of all the theorems. Implementations would be selected for inclusion based on abstractness and efficiency. Just like in the IRMT, we should select inclusion based on their general usefulness. These are theorems and algorithms, which are the most used. Right? So if anybody's Googling, unfortunately, there's no IRMT. Why? Well, building a cohesive foundation is hard. It's a really hard problem. There have been many shots in history. Examples, Euclid's Elements, Principia Mathematica, Isaac Newton, Giuseppe Piano's, heard of piano axioms, that comes from Formularum Mathematico. Nicholas Bourbaki, set theory and kind of new math, that comes from Nicholas Bourbaki, so that's Elements de Mathematique. And I think the latest effort we have that's pretty far along is Eric Weinstein's Wolfram Math World, which is a great resource and a great collection. It's not nearly, it doesn't have half of what's listed above there yet, but it's actively being developed. So it might get there. Computer science foundations, we're kind of in a similar state. We have the art of computer programming, which Don Knuth continues to work on. I don't know how much longer that will last. Communicating sequential processes from Tony Hoare. That's the foundations for most of what we think of as concurrent programming. I had to put Elements of Programming on here by Alex Stepanoff and Paul McJones. That's the book that lays the mathematical foundations for generic programming. And Wikipedia's list of algorithms is kind of similar to what you see on Wolfram's Math World. That first appeared in 2002, at least according to the Wikipedia history. And it's getting interesting, right? It's building up. For libraries, well, we still have the standard template library, and the standard library continues to grow a little bit. We have some auxiliary libraries, like the Booth Graph library, which has been around for a long time, which kind of follows this form. The Ranges V3 library, Eric Niebler's work, I think is in a similar vein, a similar category of work. But it's not a lot down here. Okay. So the language challenge, one of the things that Alex mentioned on that slide was that he's had no impact on the development of the language. Well, that certainly has changed quite a bit. The semantic constraints are still not expressed in any language that I'm aware of outside of maybe Daphne, which is a theorem-proving system. There's some significant trade-offs that come into play when you have languages like Swift and Rust that do separate compilations of protocols and traits. A separate compilation of protocols and traits, which are their names for concepts, basically, impacts your ability to specialize. So none of those languages have good specialization support. The concept mechanisms that we have in all of the major languages that have adopted this generic programming style are used for implements as opposed to models. So if you look at, in C++, we have a concept named copy constructible. That's not a concept in these terms. That's a concept fragment. There's nothing connected to it. There's no definition of it that says that the copy must be a copy, that copies must be equal. Similarly, Rust has a trait for sub, for subtraction, which is really just implements operator minus. It's not connected to addition, for example, and you can't have subtraction without a definition of addition. And also in Swift, you have things like hashable, which is really part of regular and is another concept fragment. And then there's still a huge, even on the C++ Standards Committee, a huge amount of confusion over what Alex referred to as the domain of an operation, because we have the term. It's a term borrowed from mathematics. But what happens in C++ is we tend to think of the domain of an operation as being the domain of the function signature, of all the values that you could, valid values that you could pass as the types would imply to that function. But it's really not. It's within the constraints of a precondition that you can pass. That's the domain, what meets inside of the precondition. And so when you're in the space where you're talking about requirements of an operation, what you mean by the domain of the operation is that the semantics hold for all the values you do pass. And it's a requirement that you only pass values where that requirement holds. This is why we can say operator less than on double models a strict weak ordering, even though operator less than on double is a partial ordering if you include nan. Okay? So in generic programming, it's still a model. The rule here is it's an existential exists. There exists a set of values that you can pass to that operation for that operation to model the concept. So, current design of large systems. We start to construct things in terms of objects. I think the object-oriented paradigm still dominates today. We message between those objects, which is forming incidental data structures and incidental algorithms. We use design patterns to try to reason about these systems. And we try to make sure that local rules give us correct algorithms and correct structures. Okay? And then we just iteratively refine our systems until it's good enough and we can ship. So here's a generic algorithm for building systems. Right? Identify the components and how they connect and interrelate. Right? Don't just start connecting objects together. Identify what those are. Avoid incidental data structures by packaging related objects as parts of a whole. So anytime I have related objects, I want them inside of a whole. Okay? So I want one class that contains parts that are somehow connected. This is an idea that comes out of STL. If you see before STL, the common way to have a linked list is I would have an object and it would have a next pointer in it that would point to the next node in the list. And Alex's observation was, no, 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 you want that packaged into a whole. You want stood list, which hides the invariance of that class and ensures that you have a linked list under the hood. Okay? So it's the whole's responsibility to maintain the invariance of the relationships between the parts. And we want to avoid incidental algorithms by recasting them as explicit algorithms, right? If we have the actual structure, then maybe we have a container that's a hierarchy, then we can write a function that's depth-first search on that hierarchy, as opposed to saying, well, I'm going to call this method on this node, and it's going to call a method on its children, and they're going to do something and call a method on their children, and oh, hey, look, it happens to implement a depth-first search, but there's no piece of code anywhere that tells you that. And so then we want to identify common structures and algorithms and refactor them into generic components that's common within the system we're building, and repeat, and iterate and repeat. And so this raises the question, is generic programming sufficient to build software at scale, kind of Google scale? Right? And here's the conjecture. All problems at scale become a network problem. And what do I mean by a network problem? It means that the problem as a whole becomes so complex that you can't look at all of the components and reason about it. It's bigger than one brain, and reason about what it's going to do. You have an increasing amount of relationships, and you have emergent behaviors within the system. So what you have to do is take a step back and say, how do I design and build a system such that if I follow the rules locally, then I can guarantee the global behavior. And so that's a network problem. How do I structure things so that I can reason about it on local parts, and when I have a million parts, it's going to do what I want? And that brings me to this notion of declarative forms. Okay. The idea of declarative forms is has its roots in this paper. So this is a Turing lecture from John Backus. What year was this? I know I put it in my notes. 1977 is when John Backus got the Turing Award, and he gave this lecture. And in this paper, he identified 5 compositional forms. And these were fairly simple things. They were composition, construction, conditioning, which we would usually cast as a conditional these days, iteration, and recursion. And so these were his 5 identified functional forms. Now those are actually fairly primitive theorems, and they're not even a complete basis for doing computation. His idea was, out of that, you just had these 5 common things, you could build anything else. So in reality, what you need is an infinite number of theorems, but you might have a dozen common ones sitting at your bottom, 2 dozen, 5 dozen, 100, right, something like that. So the idea of functional forms was, I think, on the right track. You can also trace the roots all the way back to this paper that came out in 1965. I'm actually slightly older than this paper, which was titled The Next 700 Programming Languages by Landon. Landon's work still influential today. He's the person who coined the term syntactic sugar, like in '64, maybe a year before this paper came out. Go look up this paper on the web. It's very beautiful, and what you'll see is a lot of the roots of Haskell and Scheme and functional programming in this. And his idea, the reason why it's titled The Next 700 Programming Languages, is basically what we want is to create a language within which it's very easy to develop DSLs to solve domain-specific problems, and that's where the next 700 languages will come from. And so the idea of declarative forms is that we can describe components by their structure and constraints in a domain-specific language. I kind of refer to these as fourth generation, fifth generation languages, right? Fourth generation languages are things that are logic languages, like Prolog is kind of the canonical example. And fifth generation languages is when you get into kind of domain-specific languages sitting on top of that. So we kind of want fourth generation, fifth generation languages. The DSLs in this space should not strive to be general purpose or Turing complete, but Turing completeness or effective Turing completeness is nearly impossible to avoid, so it also shouldn't be a goal to sidestep them. Examples that you would probably be familiar with that I think fall in the category of declarative forms are Lex and Yak, right, which are parsing technologies to describe either a lexer or a parser. SQL falls in this category, which is how we typically communicate with databases. HTML, if we kind of ignore the script tag, falls into this category, right? I write a high-level description of my page, and it resizes correctly and flows correctly, and I didn't write a whole bunch of code around that. Type systems themselves and schema-based languages fall into this category, and spreadsheets fall into this category. Right? So, what's a generic algorithm for building large systems, right? We were looking at just building systems before. Well, we apply the algorithm before for building systems, right? We write these generic components, and we assemble them, and we get to the point where that's not enough. And then we start to identify the common rules governing related parts and components, okay, and their structure. And then we choose a DSL that allows you to define the components by expressing the structure and constraints. And if a DSL doesn't exist, we develop one, and we repeat. So this kind of moves us into the next level on building a system, right? Writing your own DSL, currently pretty hard, okay? There's this underlying premise of all of this, which is that rules exist, right? I talk to engineers all the time who say, oh, this generic programming and stuff is interesting, but you know, in my job, I don't do algorithms. And I'm like, then you don't write code, because all code is an algorithm. But I hear that a lot, and what they really mean is they are writing code at the bare language level, right? They probably have for loops in there, but they are calling functions and writing an occasional for loop, and I refer to it as Dick and Jane programming, right? They are programming with a very limited vocabulary. Okay, I don't know how many people get the reference to Dick and Jane. It's a primary reader for very young children in American schools. And so it's like every Dick and Jane book has like 100 words total for the entire book. Okay, and people program like that, right? They write even large systems like that with a very small vocabulary. And so my premise is, just like in generic programming, it's the discovery that the rules exist. In large systems, the rules exist. If you're writing code and you're saying, I'm not using algorithms, I don't really use data structures, I'm just plumbing things together, just take a step back and it's like, what are you building? What are you plumbing together? There's a structure there, and there are rules that govern that structure, and there are algorithms on the messages that you are sending throughout that structure, okay? And if your system works or doesn't work depends on whether or not you are following the rules that you're probably not even completely aware of, okay? So you have to step back and say, how do I look at the system as a whole? How do I extract that information? And how do I get into something that I can reason about? So 20 years ago, I gave a demo of a system I had been working on called property models. And I gave this demo, I'll show you again, and repeat the demo in a moment, where I put up this mini image size dialogue. This was a very simplified version of the full image size dialogue at the time from Photoshop. And you just have a few things going on here. We can display width and height in terms of percent. There's a little checkbox to let you do that. And we have a constrain proportion checkbox that lets you constrain the proportions of width and height to the original document width and height. height. And that's all there is to it. And I asked Mark Hamburg, who, like I said, he's a brilliant engineer. I still work with him today, absolutely brilliant. I asked him to write the code for this, not the UI, just the code for the behavior in a language of his choice, whatever he thought was easiest. So somewhat like the binary search problem. He could do it however he wanted to. And make it as clean and efficient as he could and send me the answer. And this is the code that he sent me for that. The part that's in the gray is basically the part that's ensuring that the constraints within that little system are maintained. Okay? And the rest of it is plumbing through event handling. Okay? It's written in Objective-C. It's using, because this was from 20 years ago, it was using Apple's AppKit framework at the time. And so when the engineers tell you, well, I don't use algorithms, I just plumb things together, this is the type of code that they write, right? It's clean code. It's well factored. I see code like this all day long. How many people staring at this little tiny type think, yeah, that looks about right. Yeah, okay. If we plot out the event handling in this system, it kind of drives you nuts. I also threw in one more box at the bottom because in Photoshop we can do recording and playback, so we have a script validation piece. But we have this dialog setup code, and it propagates these fields for height and width and percent and constraining proportion checkbox. And then we have these event handlers, and they're all connected together like a big ball of spaghetti. And that's the code that Mark wrote. I literally took this from taking apart his code. Okay, so let's give a short demo here. Of course, my app quit. Hopefully just suspended. No, it did not. It's going to reboot. So I will give you a moment. I don't know, we're on the slide. Let me end show for a minute. I see what's happening. I'm just watching the VM reboot here, so you're not missing anything. I'm trying to figure out how to throw this onto the other screen. Yeah, let me see here. There's got to be. There we go. And hopefully that works. There we go. Now I'm going to have to do this not mirrored. And we'll see how we do. Let's see. This was already running, but it died. Okay, so there's the image size dialog that we saw before. Okay, and we could play with it here. We could say 500 so the constrained proportions are correct, and we can change it from any side. And if we turn off constrained proportions, then if we change one, the other one doesn't update. And we can display them in percent. also constrain proportions, and now they're like that. So you get the idea. That's the behavior. Okay. So the description of this is here. This is a little language called Atom. You'll have to approach me sometime for the history on the name. Got a bunch of papers written on this called, they're called property models. But the basic idea here is the constraints fall in as a relate clause, and constraints can be conditional. So that's when the constraint Boolean is checked. And then within one of those relate clauses, each of these expressions is a constraint satisfaction function. Okay, so this is saying that we will either solve for width in pixels or we'll solve in width percent. And we're very explicit about how we resolve the constraint. Okay? And so these are just a bunch of two-way relationships connecting the system together. Sorry. Did not mean to cough into the mic. Now, if I can find my cursor here. Now, that description is independent of the UI. So we could pull up an additional implementation of the UI, and that shows the original document there. And we've got width and height in pixels here. And you see when I type there, it changes in the other dialog box. And so if I turn off percent, then those values match. So I can have as many views on that model as I want, right? So the underlying model really has nothing to do with the UI. It's a statement of the problem of the relationships between those values. And to give you an idea, this is the full image size from Photoshop. Okay. And the reason why I coded this is and the reason why I use it as an example, is Thomas Knoll, the original author of Photoshop, wrote the code for the original image size. And for the first several years that I worked on Photoshop, we just had a stream of never-ending bugs. And most of them were deferred bugs because they were minor bugs, cosmetic bugs. There were things like if you toggled constraint proportions back and forth, the values would eventually all zero out. They would just keep decrementing down to zero. Or they were issues like if you came in here and you said, what's a good one here? That I'm not scaling styles. No. That I'm not resampling the image. You see it dimmed out these above things with those values, and it would dim them, but they wouldn't necessarily have the right value, right? Or if you see, if I'm not resampling, it dims the constraint checkbox and it undims scale styles, but scale styles would be dimmed, but it would still be checked. Okay, so even though the implication here is that it's false. Now, if you look at the description here in the same Atom system, you have, this is hard to do backwards. It's about a page of code, if I were to expand the whole thing. You have a similar thing. You've got two-way relationships. I think there's a three-way relationship. There it is. There's a three-way relationship down in there. So you just have this set of relationships that describe how all of these values are connected. And there's nothing in here that says disable or enable anything, ever. Okay? So what's the rule for when a checkbox should be disabled? There are actually two rules for when a checkbox should be disabled. So the first is when it's disconnected from the result. So it's a don't care value. Okay? In which case it should be disabled and show whatever value it had. The second case, what you're seeing here, is its value is implied by something else in the system, and there's no contrapositive, so you can't backflow that part of the graph. You can't change the value and have it undo the other thing. There may be an expressible contrapositive if I added another term in one of my relationships, but there's none expressed. So there's no way to get out of that state. In which case, it should be disabled, and it should show its implied value, right? So the widgets here, they're enabled, disabled state, what's updated with what, is just all driven by this small set of rules. So let me see. Oops. Gotta get my cursor back over here. It worked. Okay. So this was the mini image size that I just showed you, right? So you can see it a little bigger there. So just a couple of relationships. There's just 3. This is what I'd like to get it down to. So after 20 years, I've kind of returned to this work. So this is what we're trying to get it down to. I'm collaborating with Dave Abrahams on this. Right now, this is just pseudocode. We're working on the runtime for the system. So one thing you'll see that's introduced here is this is a typed system. The previous system was dynamically typed. This is statically typed, which is another form of layering constraints. And one problem that we found, the other system's been in use for 20 years at Adobe, is that people have a difficult time with a dynamically constrained system, and they end up with values that they don't expect, strings when they were expecting a number, things like that, which will lead to weird error messages. So this was the code before, right? So, I mean, we've gone from that to this, so that's pretty good. And this is the structure that we're actually building, right? So it's not a complicated structure if you look at it this way in terms of the relationships. The idea here is each of these are values. Those are our value cells in the boxes, and the circles represent relationships. Okay, and the arrows are a hard arrow, meaning that there's only a single flow in there, and the empty arrowheads mean that the actual direction of flow is going to be determined by a priority system and by what these relationships are. Okay. So, future software development restated. I think we need to continue to extend the ideas of generic programming to more domains. I think we're still making slow progress on generic programming. We need to extend generic programming to apply to runtime polymorphism. I left that on there because we're not quite there yet with protocols or traits, specifically because we don't have good mechanisms for specialization. And we need to formally describe software behavior by expressing the structure and constraints of the system. Right? And it's not just property models, which is what I was just showing there, but I think there's a class, a handful of kind of base functional forms. And another one is how do you describe the constraints and relationships on manipulating sequences? One of my colleagues, Jaakko Järve, who's a professor in Finland, that's something he's been publishing a number of papers on recently. So some references for property models, if you want to take some shots. These are some papers that have been published on the idea. There's my implementation. There's a JavaScript implementation. There's a Rust implementation out there now. So it's making, there are several libraries that do this. Some related work. Jaakko and I published a paper on selections, like how you select in the UI collections of objects within a UI in an any-dimensional space. And because what we found is all the UIs out there kind of work as coded, right? There's this notion of, oh, if I shift-click, it extends my selection, and some software does that by XORing, and some software does that by taking the last item you clicked on, and some software does it by taking the whatever the surrounding item you clicked on was. So we had started working on the problem of containers for UI modeling, and realized that nobody had really defined the calculus for selections. And so Jaakko and I sat down and wrote that paper. I think it's a good paper. And then this is mostly Jaakko's work that he's been doing in my absence, since I've been shipping products for the last 20 years, nearly. This is mostly work around how do you model sequences. Okay. So we want to continue improving generic programming support in languages. We want refinement. We want dependent concepts. We want law of exclusivity, which is what follows from whole-part relationships. We want to minimize, that's a Rust, or that's a Swift term, but it's borrow checker if you're a Rust person. It's single exclusive access. We want to minimize trade-offs between efficiency and safety. We want to create better foundational libraries by implementing fundamental concepts and algorithms, and I'm hoping that C++ will get to the point where not everything has to go in the standard library. I've got this little side project going on GitHub/STLab, which is kind of a minimum shell for doing a C++ framework with documentation and unit tests and kind of modeled after what you would get if you installed the Rust tools, but for C++. And I'm hoping to turn that into a better mechanism that you can just build little mini libraries and have them easily distributed and have them composed together, much like you would have with Cargo in Rust or the Swift package manager in Swift. But in C++, we've been left out in the cold. We want to create libraries of embedded DSLs, and these want to interoperate with the underlying language. I'm speaking at a C++ meetup, but I'm actually doing most of my code these days in Rust. And so the framework that we're building for building DSLs is actually DSLs that interoperate with the underlying Rust language. So any type or function that you can express in Rust, you can export it into the DSL and use it within the DSL and the DSL expressions. And then we want to develop AIs that can reason about the code so that it can continue the above. And if anybody's, I'm sure all of you have used the current AI tools, they tend to be pretty hit and miss with C++. They do a good job with binary search, but with general problems, it's here or there. I found they actually do really good with theorem proving systems. So if I write code in Daphne and I ask it to complete a proof, and it will say, oh yeah, you're missing this loop invariant right here, and if you insert that, now your code, we can prove it's correct. And that's because in order to compile Daphne code, it has to be correct. It has to be provably correct by theorem solvers within Daphne, which means nobody checks in code that doesn't compile. So all the code that the AIs have learned from has been Daphne code that's checked into GitHub, which is all correct. And so it does a pretty good job with that. I went back somehow. So that's it. I think I might have run a little over. I will take questions if anybody has questions.
No questions?
No questions.
Yeah.
There's one up here.
Yeah. Thank you for the talk. The question is, I assume Photoshop has lots of dialogues, so it makes sense to build a DSL to make it easier and, well, more correct. But lots of tasks we do are not like that. They're more like one-off thing you do on the program startup. And I assume it doesn't make sense to build a DSL for one-off task because it will actually be more work and more layers of complexity. So the first part, do you agree with this? And if yes, then I think the most important practical question is, what is the threshold in the complexity of the system at which point it makes sense to invest in DSLs in their more explicit expression of concepts and relations and like increase the complexity of the system and
Yes.
Yeah.
I think it's, well, first right now, other than there are good libraries for a handful of DSLs out there. So if you want to write a parser You probably shouldn't write your own. There are lots of parsing frameworks out there which will take an EBNF or EBNF-derived grammar and spit you out a parser for it with different performance characteristics. So a lot of these systems already exist. And unfortunately right now, I think writing a new DSL and writing a new DSL that operates with your underlying language is a pain. It's a problem, and it adds a lot of complexity. So, I occasionally these days, I will roll my own parser, even though there's great parsing libraries out there, because I need my semantic actions to be interfaced with my language, with my code, and I want to talk about it in terms of my types, and I can't do that in my EBNF grammar. And so that's one of the problems that we're trying to solve, is to lower that barrier to make it easier. But the process here is still one of kind of iterative discovery, right? If you're down and you're looking at the code and you're doing a lot of plumbing and you're thinking to yourself, I wrote this code yesterday, right? How many people feel like that for a bunch of code that they write, right? I know I do. It's like not identical code, but it's the same code, right? I wrote it yesterday here, I'm writing it over here, I'm writing it like that over there, and it's the same code. That means there's some kind of underlying structure under there. There's some kind of underlying rules. And so you have to take a step back, and you have to say, okay, can I describe that? Is there value for me describing that in my product? Maybe not. Maybe it's probably worthwhile understanding the structure that you're trying to create, but there probably is not value in trying to create a DSL within which you can solve the whole problem. But if you can understand what the problem actually is, if you can draw it, if you can reason about it, if you can draw pictures, that will improve the code you're writing. Doing things like, I say never use a pointer in an interface, certainly not a shared pointer, right? How many people here have shared pointers in their code bases in most of the places? Yeah. Okay, so what's the problem with a shared pointer? Well, there's no clear ownership. There's no guarantee that I have exclusive write access to this thing following the borrow checker, and that breaks local reasoning. That means when I'm reasoning about a piece of code and I call some function, am I 100% sure that that function isn't going to change this object out from under me, right? What do I actually know about that thing? And you might say, well, I know because I wrote this other code and I wrote that other piece of code. Okay. Well, even if you can keep it in your head, that doesn't scale. The next guy you hire is going to screw it up. Okay. So you have to keep saying, how do I get rid of this? The other thing about pointers in an interface is they're ambiguous. Is the function operating on the pointer or the thing the pointer points to? So you immediately raise an additional question there. So even if it's a unique pointer, it's like, am I passing the unique pointer? Am I handing off ownership? Is the thing that I'm passing it to just going to read it? Do I want to go look at the signature and say, is it passing by const reference versus pass by value? No, I just want to look at my code and reason about my code locally, right? So pointers raise this extra ambiguity. So it's those kinds of things. It's the I've got objects with pointers to other objects in them. That's a horrible thing. What structure does that create? Is it a graph? Is it a hierarchy? Is it a list? A network? What kind of thing is it? What rules govern it being a correct thing? Who's enforcing the invariance? Who's making sure that that thing does always form a hierarchy? And again, you might say, well, I know it always forms a hierarchy because every time I add a pointer to a child, I also set the parent back pointer, and so it's always a hierarchy. Until the next guy you hire who screws that up. So those are the kinds of things you want to be doing. And then looking, parsing, I bring up parsing a lot. Parsing and databases are like two things that most engineers don't recognize. They don't recognize when they're working on a database problem and just use a database. And they don't recognize when they're dealing with a parsing problem and they write a bunch of regex expressions instead of just writing a recursive distance parser. So you have to have enough vocabulary to learn those names. So right now, I'm not saying that I'm recommending to all of you, go write your DSLs. Unless you're working, if you're working at Google, if you're working on a system at scale and you're seeing very large patterns, man, go write those DSLs. That will multiply your organization's effectiveness by a massive amount, okay? What I want to do is come back, hopefully not in 20 more years, hopefully a little sooner, and be able to say, here's how you can write your own DSLs. Here's how you can do that. So, not there yet, but that's the goal. So, a very long answer to one question.
Yeah. So I will abuse my power. So I work at Google, and we have a lot of DSLs, I think.
Uh-huh.
And the problem that I personally have is that, so we have a lot of those layers, right? So we have one DSL that kind of lay out the foundation. Then you have another DSL that helps you combine different things. And then on the next level, you have another DSL. But the problem that I'm having often is that this DSL on the top level lacks the ability to pass something to the really low level. And sometimes you just need to do this, right?
Yeah.
So I'm not sure if it's because we actually don't know how to create proper DSL, or is it this problem about all the problems in software development can be solved with one more layer of abstraction, right?
Yeah, yeah.
So it just seems to me that with the complexity, so I agree with the UI, I can see that even if it's complicated, it can be probably more clear defined with a declarative way. But sometimes when you have this system that you then use to build another system, and this system is used to be another system, and then you have some kind of configuration, it just becomes also a mess,
Right.
even in the declarative way.
Right, and that goes back to the Landon paper I put up, the next 700 programming languages, which is the state we're in right now is I think most of the DSLs that we have and that we use don't look at all like each other, and they don't interoperate with any underlying language, right? Or they only operate with some specific thing. So HTML marginally interoperates with JavaScript. But a lot of times we use HTML on top of a C++ backend or on top of a Rust backend. That's not so great. Okay. Parsers, we get down to the point where our parsing language looks nothing like our semantic actions in whatever language we're writing them in. Within HTML, an expression in HTML doesn't look quite like an expression in CSS and does not look like an expression in JavaScript. Right? So we have the same concepts even within one ecosystem, and we have multiple different ways of representing it. And then it becomes a challenge to make them interoperate and plumb through. So you really want a substrate. One of the things that I did with the Atom stuff that I showed and the Eve language, which is the UI layout language that sits around it, is that it interoperates. It's dynamically typed, but kind of like Studini is dynamically typed. It interoperates really well with C++, which is to say if I want to add a new function, I just register a C++ function, and it gets wrapped up to say, because it's dynamically typed, it's going to take anything, but then we're going to take it out to the actual argument signatures, and it's going to return in anything. And so I can introduce a function that's basically a constructor for a type, and then I can introduce operators on that type, and now I can do it. So I can have, when you slide this slider, Gaussian blur my Photoshop image. I don't have to express the Photoshop image in my DSL. I just need to know how to send the, call the Gaussian blur method on my Photoshop image. So you need that connectivity. Like I said, sometimes I hand roll my own parsers. And it's like, there's great parsing technology out there, and I usually write a Nicholas Wirth, talking about ETH, a Nicholas Wirth style recursive descent parser. Huge Nicholas Wirth fan. So, yeah, I mean, there are these great systems out there, but they don't plug together and they don't interoperate, and you hit those things. You know, if you've ever been like, oh, geez, I got to construct a string to pass to SQL, right? It's like I have to write an SQL expression. It's like you're sitting in C++. You have a language that lets you write expressions. Why can't I just write C++ and hand that to SQL and have it do my query? That's what you want.
So I have a question following on this DSL. What would you say is the amount of effort you had to spend on the language aspect of Eve versus the engineering dimensions of it? Like you have to have a syntax highlighter, you have to have a code formatter, you have to have a debugger. So what would you say was the ratio of effort between the two?
It was 100% on the language and 0% on the other tools, because we don't have the other tools. And that's a huge problem. When I'm working in Rust right now, there's a Rust library you can look at called RSX, which the Rust macro system. How many people have programmed in Rust at all? Okay, about half. The Rust macro system is insane. Who here has ever written a Rust macro? Okay, about half the half. Rust macros basically give you the Lex stream and let you generate your own code out of that. And there's some significant pros and cons to that, but one of the pros is that if you're a little careful about your syntax, all the existing Rust framework will work on those macros. And you can run them runtime, you can run them compile time, it doesn't matter, and you get all the syntax highlighting in your IDE. So I can show you, like from the framework that we're building right now, if I get an error message in my debugger, then it looks like a Rust error message, and if I click on it, it takes me to the right line of the code, and so we're solving all of those problems in a different way. But there is additional tooling that we're building around it too. Like if you look, one problem that people have with property models is the system provides a very strong set of guarantees about basically that once you describe a system, it will guarantee that for any values that you plug into that system, there's a solution, there's a flow through the graph, and there's a little model checker that goes along with that to do the proof. The problem with that, as with a language like Daphne, is you write a piece of code and the compiler tells you, well, you're wrong, and it's very difficult to iterate and to see what's going on. So one of the things we're working on is how do we draw a graph of the structure you're building, and so even before you have a working system, we can show you a partial graph and show you where the graph breaks. So you need tooling like that. So the prior system, our investment was 0. We have 20 years of experience saying that that's been a big mistake. So I don't know what the ratio will be this time around.
Thanks for the talk. I've been wondering for years if software engineering as a discipline will ever graduate to the kind of same level of certainty of operations as other disciplines of engineering. I mean, we understand spring and damper systems to a level that make it very predictable when I'm developing a new car. And I wonder what's your opinion. Will we ever get there, especially with adding complexity on top of complexity as we are doing at an ever faster rate?
I don't know. It's, I mean, still a possible future. I'm not making a prediction here. One of the challenges we're facing right now, back in 2006, when I put together this talk, we were in the middle of what I refer to as the Java Dark Ages. And what I mean by that is universities were teaching almost nothing but Java. At least American universities were teaching almost nothing but Java. And there was a whole group of graduates who didn't know how the machine worked. Okay? They didn't even really know how the virtual machine worked. Okay? It got so bad that before anybody got to the binary search problem, um, I would start talking with candidates, and it was very clear the interview wasn't going well, and I would send them home, and I would talk to them first and send them home. And the recruiter said, "You can't do that, right? These are new grads. That's a horrible thing. You just, crushed them." She said, "Is there something that I could ask these students?" And I said, "Yes, ask them to give you a binary representation of -1. And the recruiter said, "Well, what's the right answer?" And I said, "I don't care." If they give you something like I said, even if they ask you a question, if they ask something like, "Do you mean sine magnitude or 2's complement?" Man, send them to me, okay? Okay? But if they can't answer, okay, even with some feasible question, then I don't want to talk to them. One of the answers I accepted was, okay. I said, the recruiter actually called me up and said, so he made this like F sound, like. Do you want to see him or not? I said, I'll see him. Okay. I have several colleagues who think we are entering the AI dark ages, okay, where people are writing code with LLMs, and they don't have any understanding of how the code works, and they certainly don't have any understanding of how the underlying hardware works, and they are producing AI slop. And so even though the AI is very good at generating a binary search, for the most part, AIs will generate sub-median code very rapidly, okay? And it might even get to the point where it's generating median-level code very rapidly. That rapidly part is a problem, right? All of your code is a liability. Every extra line of code that you add to your product is something somebody has to understand and maintain and update and all of that. So, the analysts are saying this is the future. I'm like, it's a scary future. My hope is we can turn that around. We can use that power to say, how do we write correct and efficient code? Okay. And if there's going to be an impetus to do that, to get us on par with, say, mechanical engineering, it's going to come through legislation, right? It's going to come through the legislation that there is for memory safety, that's pending, may never pass now in the US, unless we get a new administration, which may never happen. But it will probably pass at some point in the EU. And over time, I expect increasing liability for companies that ship buggy software, and that will be liability typically comes with a triple penalty if you knowingly shipped a defective product. And so I think those rules are going to start to apply to the software industry, just like they do with every other industry. And that in turn will lead to process and education and certification and a whole bunch of unnecessary bureaucracy for trying to achieve the code, but it will get us there. So probably, eventually, I hope, but I don't know.
Thank you for your talk. You mentioned theorem proofers a few times already. I'm wondering, do you think like the theorem proofers, systems like Daphne you mentioned, but also like Rocklean or whatever, will they get more important in the future? Or is there maybe, since they're relatively radical, right, parts from these theorem proofers that we can incorporate into our traditional programming languages, so specifically thinking a lot of the syntax for expressing like preconditions and postconditions?
Yeah. I think they will become more important and more practical. There are a number of interesting systems. I'm horrible with names, so like the only thing I can come up with is the stuff I'm using, which is Daphne. But there are a number of similar systems. Most of them are still kind of researchy. Daphne is probably the closest thing that I've seen to generating production code, which is Daphne compiles into a number of languages, including C++. There are certainly more mature systems like TLA Plus, which is great for proving consistency of your specification, but doesn't really do code generation at the back end. So I think that those are going to become more important. I also think that LLMs, if those systems are to gain in popularity, LLMs are going to play a role in that, because there are fundamental limitations to kind of automated theorem proving. And it is really frustrating to be looking at a piece of code and you know the piece of code is correct, and you have tried your best to tell the system that that piece of code is correct, and the theorem solver is basically saying, I don't believe you. Okay? It's like, what do I need to tell you so that you can complete the automated proof? There's not enough input there. LLMs are really good at extracting the patterns that they've seen of these systems and being able to say, oh, you need a loop invariant. You need a termination condition. You have a loop invariant. You're missing this other loop invariant. You stated your precondition, but the postcondition doesn't match, or I can't verify the postcondition because of foo. So LLMs are really good, I found, at picking those out and telling you exactly, like, you need to say this here. And then you're like, of course, right? Why didn't I think of that? So I think there's a definite role there. And so that's on the, can we avoid creating AI slop super fast and somehow bend these tools to create correct and efficient software faster? I hope. Any more questions?
Let's do the last one.
One down here.
Can I just, again, abuse my power?
Sure.
Just get back to the automotive, for example, and the flying industry. There is a MISRA standard, right? So we're actually already moving to this bureaucracy, and you cannot just develop software for automotive industry. You need to pass the certification, and it's quite complicated, actually.
Yeah, he was mentioning MISRA. There's a number of domains, if you're in the aerospace industry, if you're working for a government, Department of Defense, they have their own set of processes. I can tell you some bizarre stories about that, but.
Hey, thanks for the talk. It was really awesome. I'm a big fan of generic programming, but as you said, and also as Alex himself has said, unfortunately, it hasn't really taken off. It's been around for a long time. What do you think is the main reason that it hasn't taken off?
I think certainly it has come a long ways from where Alex was, and in part through Jeremy Seek, who worked on Rust traits, and he worked on the C++ OX concepts with Doug Greger. And he and Doug Greger then did Swift protocols, and we have C++ concepts in the language. So the ideas have spread much further. They're getting much more adoption than they were 20 years ago. But fundamentally, it's math, and math is hard. When I put up the axioms for equality and copy, I have engineers at Adobe who tell me every time I use a math symbol, I lose 10% of my audience. I think that's very unfortunate. My math chops have never been great, but I had the pleasure of learning from Alex for 8 years. But yeah, I think one is we need to get over the fear of mathematics. I go into the other thing, we need to get more formal in our approach to software development, and that's kind of through mathematics. And but there's no easy way, right? I've been teaching this stuff for more than 20 years, and there are now many more people who are involved in generic programming than there were 20 years ago, but it's still a small fraction of the community.
Sean, thank you again for giving this amazing talk.
Okay.
Thank you for coming. Sorry. I think we can hang out just a little bit, and we can take all the rest of the questions offline, if you're okay with this, because it's what time is it in California right now?
It's about noon right now.
Oh, okay, so
12:20. So I'm awake again, I guess.
okay, thank you so much.
Yep.